Okay, think about that moment during a powerful thunderstorm.
Mm,
The sky rips open with a blinding flash. And then, well, after a short delay, that deep rumble or maybe even a sharp crack of thunder hits you.
right, that immediate visual impact.
Exactly. And when you see that flash, it really looks like a brilliant line, shooting straight down from the cloud to the ground. It feels instantaneous, like just one single powerful bolt.
That's definitely the common perception. It's the part that grabs our attention, the most, well, dramatic element. Our eyes are naturally drawn to that incredible brightness.
It is the spectacle. But what if I told you that familiar image, that single bolt, seemingly instant cloud to ground, is actually just a tiny snapshot of a much more intricate, really complex, and often kind of counterintuitive process?
Ah, yes. The physics behind it is fascinatingly complex.
We've been diving into a whole stack of sources for this deep dive research papers, detailed scientific articles, complex diagrams, and they paint a picture of how a lightning strike really develops that is so much richer and frankly stranger than just that simple visual.
Absolutely. The material we looked at reveals it's anything but a simple single-step event. These sources carefully lay out this whole sequence of interconnected events. There are multiple types of electrical discharges, distinct stages,
Hmm.
and some of it happens so fast or it's so dim that our senses just can't pick it all up in real time.
And one of the first things, maybe the most surprising thing these sources challenge right away, is that basic idea of lightning just traveling down from the sky.
Right.
There's this core question in one of the articles. Does a stroke between a cloud and the ground actually travel upwards or downwards? And, well, maybe unexpectedly based on what we see, the answer, according to all the science, is surprisingly both.
It's a duality, isn't it? It really underscores the complexity of atmospheric electricity and the sheer power involved. It forces you to rethink that immediate visual impression.
So that paradox, that's kind of our starting point, our mission for today. We're going to do a deep dive into the real physics of a cloud-to-ground lightning strike. We'll meticulously unpack the hidden steps, the stuff you don't see, the truly incredible speeds at different stages, and just the raw, immense power packed into this awe-inspiring natural event.
Using the comprehensive material provided, yes.
Exactly. We're building this understanding based entirely on that material. So get ready to move beyond just the flash and the boom and really get into the science happening inside that split second. So if we're tracing the journey of a lightning bolt, where does this whole dramatic, complex sequence actually kick off? Way up there in the atmosphere.
Fundamentally, it all begins inside the thundercloud itself. The sources really emphasize this crucial process of charge separation that happens within a mature, vertically developed thunderstorm. That's the engine driving the whole thing.
And how does that charge get distributed? Is there like a standard layout inside the cloud?
Yes, the sources consistently describe a pretty characteristic pattern in a developed storm cell. You generally find a large accumulation of positive charge way up high in the upper parts of the cloud, often spreading out into the angle.
Okay, positive up top.
Right. Then below that, in the main body of the storm, and specifically concentrated in the lower portions, you get a significant buildup of negative charge.
Negative lower down. Makes sense.
And interestingly, closer to the very base of the cloud, there's often another, smaller, more localized pocket where positive charge gathers again. So you can kind of picture it as distinct layers or centers of charge within the cloud structure.
Huh. So you've got this big negative charge region sitting low in the cloud right above the ground. That must create an enormous electrical tension, right? A huge potential difference with the Earth below.
Absolutely. That negatively charged cloud base exerts a really strong electrical influence on the ground directly beneath it. And because opposite charges attract, this causes or induces a large amount of positive charge to accumulate on the Earth's surface below the storm.
So the ground becomes positively charged underneath the negative cloud base.
Exactly. The sources describe this effect quite vividly, visualizing it almost like a charge wave that follows the storm cloud across the landscape as it moves. The electrical potential difference between that concentrated negative charge at the cloud base and this large induced positive charge on the ground becomes absolutely immense. It just builds and builds, heading towards the point of electrical breakdown in the air.
But, okay, here's something surprising the sources highlight. Even with that huge potential building between the cloud and the ground, the very first visible electrical discharge doesn't necessarily leap all the way to Earth.
That's a key detail, yes. The sources indicate that often the initial electrical breakdown, the first really significant spark, actually occurs within the cloud itself.
Inside the cloud. Between which parts?
Commonly, it happens between that main negative charge center, which is a bit higher up, and that smaller localized pocket of positive charge located down near the cloud base.
Ah, that lower positive pocket we mentioned.
Chris.
And why is that preliminary discharge, that internal spark, so important for setting up the main event, the cloud-to-ground strike?
Well, it acts as a critical precursor, sort of a trigger mechanism.
Yeah.
By discharging internally between the upper negative region and that smaller positive area near the base, it effectively transfers even more negative charge down to that specific region right at the cloud base.
Okay, so it concentrates the negative charge right at the bottom.
Exactly. It intensifies the concentration there, pushing the electrical potential difference between the cloud base and the ground below right up to the critical threshold. And that's what's needed to initiate the next major stage, the beginning of the journey down towards the Earth.
Okay, so the storm cloud is charged up, potential difference with the ground is massive, and that internal spark has basically loaded the cloud base with this intense negative charge. What happens next to bridge that huge gap down to the ground? How does the strike really begin its descent?
Right. This is where the really fascinating and often misunderstood stepped leader comes into play. The sources describe this as the launch of a downward moving electrical discharge. It originates from that intensely charged region at the cloud base.
And it launches when the electrical potential gets high enough.
Yes, precisely when the electrical potential gradient in the air just below the cloud reaches a critical breakdown point. One source actually quantifies this, puts it around 10 to the 6th volts per meter. That's an incredibly strong electric field.
Wow. Okay, so this step leader starts heading down. But, and this is key from the sources, it's typically not something we actually see with our naked eyes, right?
Precisely. It's absolutely fundamental to the whole process, but visually it's elusive. The sources explain why. Basically, our eyes and brain aren't fast enough or sensitive enough. We can't resolve the brief, relatively dim phases of the stepped leader's formation and its stepwise journey compared to the overwhelmingly brilliant flash of the return stroke that follows just milliseconds later.
So we can't easily see it. What is it then? This stepped leader probing downwards, what's it made of? How does it move?
It's characterized as a channel, or maybe a core, of negatively charged particles. It's essentially carrying that high negative potential from its origin point in the cloud down towards the Earth. But crucially, as the name suggests, its movement isn't smooth or continuous. It doesn't just flow like water.
Ah, the stepped part.
Yeah.
So it moves in jumps.
Exactly. It advances in a series of rapid, discrete segments or steps. The sources give us some dimensions for these steps, figures around 50 to 100 meters long.
Which is, what, roughly 150 to 300 feet per step?
Yeah, in that ballpark. And each one of these individual steps happens astonishingly fast in less than a millionth of a second.
Less than a millionth of a second for a jump of maybe 300 feet. That's almost impossible to comprehend.
It is. And then, after finishing a step, there's a brief pause before the next one begins. The sources put this pause duration at around 50 millionths of a second.
A tiny pause.
Yeah.
Any idea why it pauses?
Well, one source offers a hypothesis. It suggests that the tip of the leader might momentarily pause to, quote, recharge itself with more charged particles flowing down from the cloud base before it's ready to make the next leap into the virgin air below it.
Huh. Recharge and jump. Recharge and jump. So even though it's these incredibly fast, tiny jumps with short pauses, the overall effect is still a rapid downward movement, right? What's the average speed for the whole trip, cloud to ground?
Across the total distance, yeah, the average speed is significant. One source gives an average of about 75 miles per second. At that rate, it covers the typical cloud-to-ground distance in something like 20 thousandths of a second.
Still incredibly fast.
Oh, absolutely. Though another source focuses specifically on the speed of the jumps themselves and puts that figure much higher, around 450,000 miles per hour, which, if you convert it, is about 125 miles per second. So, whether you measure the average rate or the burst speed, it's definitely moving very fast, just significantly slower than the return stroke that comes later.
And all the while, it's bringing negative charge down from the cloud. How much charge are we talking about? And what kind of electrical current is involved in just this leader phase?
No, the negative charge is continuously fed into this developing leader channel from the cloud's main negative reservoir. By the time a typical step leader gets close to the ground, it might have accumulated around 5 coulombs of negative charge spread along its length.
5 coulombs.
Well,
That sounds like a lot.
it is a significant amount of charge, and transporting that downwards requires a pretty substantial average current throughout the leader process. The sources estimate it in the range of 100 to 200 amps on average. But the pulsed currents during those really rapid individual steps, they can be much higher, possibly peaking around 1,000 amps momentarily.
Okay, and what does this channel actually look like, even if we can't see it well? The sources mentioned photographic studies.
Right. Even though the actual conducting core is thought to be very narrow, photographs show a larger luminous diameter around it. Measurements put this visible luminous diameter anywhere between 1 and 10 yards wide.
Wow, up to 30 feet wide. That seems huge.
It does, but one source breaks it down further. It suggests the surrounding electrical corona discharge might be, say, 1 to 5 feet across. Then there's maybe an ionized envelope around that, perhaps 4 to 6 inches wide. And the actual highly conductive core itself is thought to be much, much narrower, maybe only a fifth to half an inch in diameter, or less than an inch according to other data.
So the bright part we might photograph isn't the tiny core carrying the current, it's the glow around it.
Exactly. That wider luminous appearance is attributed to this electrical corona, a kind of discharge in the strong electric field surrounding the intensely ionized, very narrow core.
And it's the way this step leader finds its path that gives lightning that classic zigzag shape we see.
That's precisely it. The stepped leader doesn't take a straight path down. It probes, explores different routes, essentially following the path of least electrical resistance through the air at each step.
Like it's feeling its way down.
Sort of, yes. This variability in searching behavior is why it takes on that characteristic zigzag or tortuous shape. And it also frequently branches out multiple times as it descends, exploring several potential paths downwards simultaneously. These branches are crucial because they directly contribute to the highly branched appearance of the first visible lightning struck we see later.
Okay, so this invisible, rapidly stepping, negatively charged leader is making its way down, branching as it goes. What happens when it starts getting really close to the ground below?
Right, as that negatively charged step leader approaches the ground, its immense negative charge exerts a powerful electrical influence on everything underneath it. It induces, as we mentioned before, a large and concentrated amount of positive charge on the Earth's surface. And this effect is particularly strong. The positive charge concentrates most intensely on objects that project upwards.
Like trees.
Buildings. Exactly. Trees, buildings, power poles, even a person standing out on an open field. These become focal points for the induced positive charge.
So taller objects basically act like lightning rods even before the lightning hits, concentrating that positive charge and making the electric field around their tips really strong.
Precisely. The sources describe this well, explaining how it creates a significantly enhanced positive electric field near the ground, especially right around these projecting structures. It's almost like the ground is electrically reacting to the descending negative leader, getting ready to meet it by gathering its own positive charge at the highest or most conductive points available. You can still visualize that induced positive charge on the ground as that charge wave we talked about, relentlessly tracking right beneath the negative part of the storm cloud.
And because opposites attract, this concentrated positive charge on the ground isn't just sitting there passively, right? It starts trying to reach up towards the descending negative leader.
That's the next absolutely critical step, and it's the other half of that upward or downward answer we talked about at the start. Driven by the strong attraction to the negative charge coming down with the leader, this large positive charge on the ground initiates upward-going electrical discharges.
Coming up from the ground.
Yes. These are sometimes called ground streamers or positive streamers in the sources. They launch upwards from points where the electric field is strongest and the positive charge is most concentrated, typically the tops of those collar features, trees, structures, etc.
Is that related to that feeling people sometimes describe just before a lightning strike? The tingling, hair standing on end. Could that be these ground streamers forming?
It absolutely could be. That sensation is often reported by people outdoors under a thunderstorm. They might be within this region of strongly enhanced positive electric field near the ground. It could even mean you're physically close to a point where a significant ground streamer is trying to form or has just started.
That sounds terrifying.
It should be. Regardless of the exact cause of the sensation, it's a definite warning sign that you are in a very, very dangerous location and need to seek safe shelter immediately.
Okay, so you've got the invisible, zigzagging, stepped leader coming down from the cloud, and these positive ground streamers reaching up from tall objects on the ground. Eventually, they have to connect, right?
That's the crucial moment, the attachment point. One of these upward-moving ground streamers successfully manages to meet and connect with a branch of the downward-moving stepped leader channel.
And that connection point is what determines exactly where the lightning hits.
Yes. That point of connection is incredibly significant because it dictates the precise path and the exact location where the lightning strike will ultimately bridge the gap between the cloud's charge reservoir and the ground. Or maybe better put, it's where the conductive pathway is finally completed.
And this connection, this meeting point, it doesn't necessarily happen right at the ground surface or even right at the very tip of the object that launched the streamer.
No, that's another one of those counterintuitive but really well-documented details from the sources. The actual connection, the attachment, typically occurs some distance above the ground or above the tip of the structure that sent up the successful streamer.
How far above?
One source estimates this height could be anywhere between, say, 100 and 1,000 feet up in the air. It depends on factors like the amount of current flowing in the leader channel at that moment. But at that instant, whenever and wherever that connection happens, the electrical circuit between the cloud and the Earth is finally complete. The pathway is open for a massive exchange of energy.
Okay, so the invisible stepped leader from the cloud meets an upward ground streamer, connecting somewhere above the ground. The circuit is complete. And this is the moment that generates the blindingly bright flash we actually see as lightning.
Exactly. This critical connection initiates what's known as the return stroke. Once that conducting channel of the step leader is connected to the ground via the streamer, the enormous amount of negative charge that was distributed along the leader channel, especially the charge near the connection point, begins to surge, to move violently, as one source puts it, down to the Earth.
A huge rush of charge.
A massive rush. This rapid movement of charge constitutes an enormous pulse of electrical current. And this huge current causes the air within that channel, starting near the ground connection, to become intensely heated and therefore intensely luminous. This is the brilliant, blinding flash our eyes perceive as lightning.
So wait, the bright flash isn't the leader coming down. It's something that happens after the leader connects.
That's absolutely right. The visible flash is the return stroke. And here's where that upwards motion really comes into play, addressing that paradox we started with. The region of highest current and brightest luminosity, the visible return stroke channel, it doesn't just light up all at once along its whole length.
No. How does it happen, though?
Instead, the incandescent channel propagates continuously and incredibly rapidly upwards. It starts from the ground connection point and travels back up along the ionized pathway that this stepped leader created just milliseconds before. It also shoots up along any significant branches the leader formed.
It propagates upwards. Wow, that really does feel completely backward compared to seeing a bolt come down.
It does. It sounds strange, but that's precisely what the scientific sources describe based on high-speed photography and other measurements. The speed of this upward propagation of the return stroke is just astounding. Orders of magnitude faster than the step leader.
How fast are we talking?
The numbers are mind-boggling. One source gives speeds ranging from 20,000 to 60,000 miles per second.
Per second.
Yes. Another source cites speeds around 5 times 10 to the 7th meters per second, which is roughly 112,000 miles per second. And one source even mentions that the speed of the visible stroke's upward propagation can reach up to 1/3 the speed of light.
A third of light speed. That's almost cosmic speed happening right here in our atmosphere.
It is truly phenomenal. This incredible speed is why the entire trip, from the ground connection all the way back up the channel to the cloud base, takes only about 100 millionths of a second.
So even though the bright part is moving up, the actual electricity, the electrons, are still flowing down.
That's a crucial distinction, yes. While the region of high current and intense luminosity is moving upward along the channel, the electrons themselves, the actual negative charges, are still moving downward throughout the channel, flowing rapidly to the ground to neutralize that induced positive charge there. After that initial, incredibly fast upward surge of the return stroke's luminous front, the remaining negative charge that was still on the leader channel continues to drain into the ground over a slightly longer period, typically a few thousandths of a second.
And what happens to the channel itself after this massive current pulse and charge transfer? What state is it left in?
Good question. Once the charge has flowed to the ground and the main return stroke brightness is passed, the channel, which started out filled with negative charge from the leader, transitions. It's now this ionized pathway that has just facilitated this huge flow of negative charge to the ground. And in response to the surrounding atmosphere's electrical state, it effectively becomes positively charged for a short time.
Okay, so the return stroke is the super bright part, shooting upwards at near light speeds. And our eyes just see it as one single instantaneous flash. because it's happening way too fast for our vision to actually resolve that upward movement.
Precisely. That upward propagation is so unbelievably rapid, essentially completing its journey in far less time than it takes for a nerve impulse to even travel from your eye to your brain, that our visual system perceives the entire channel lighting up all at once. It just registers as that single, brilliant flash image.
And that intensely heated, bright channel.
Yeah.
It must be creating some extreme physical conditions in the air right around it.
Yeah.
You mentioned heating.
Oh, extreme is putting it mildly. The sources provide astonishing figures for the temperature inside that narrow lightning channel. The core temperature can reach 3 times 10 to the 4th degrees Celsius,
Which is
approximately 54,000 degrees Fahrenheit.
54,000 degrees. Hotter than the sun's surface.
Yes. One source makes that exact comparison, stating the temperature can indeed be hotter than the surface of the sun, citing a specific example for one type of strike reaching 50,000 degrees Fahrenheit. It's a plasma state, incredibly hot. Fortunately, this extreme temperature is confined to a very, very narrow core and drops off extraordinarily rapidly as you move away from the center of the channel.
That kind of instantaneous extreme heating in such a tiny space must have a powerful mechanical effect too, right? Like an explosion.
Absolutely. The sources describe this process as essentially explosive. The air within that lightning channel gets heated so incredibly quickly to such extreme temperatures that it expands outwards with immense force and speed. This rapid, violent expansion generates a powerful pressure wave that radiates away from the channel.
How much pressure?
Near the core, the pressure can be incredibly high, exceeding 24 atmospheres. But like the temperature, this pressure drops off very rapidly with distance. Initially, this expanding wave is actually a supersonic shock wave, moving much faster than the speed of sound, potentially up to 10 times the speed of sound right near the channel core.
And that pressure wave, that's the source of thunder.
Exactly. As that initial powerful supersonic shock wave propagates outwards and weakens with distance, it eventually slows down and decays into an acoustic wave, a sound wave. And that sound wave is what our ears perceive as thunder.
Which perfectly explains why we always see the lightning flash before we hear the thunder. Light is just vastly faster than sound.
That's the principle, precisely. And the sources even provide that handy rule of thumb many of us learn. You can estimate how far away the strike was by counting the seconds between seeing the flash and hearing the start of the thunder.
The 5-second rule.
Yeah, basically, every second you count corresponds to a distance of about 1/5 of a mile, or more precisely, 0.214 miles. So if you count 5 seconds, the strike was roughly 1 mile away. It works because sound travels relatively slowly compared to light, around 770 miles per hour, at typical air temperatures like 70 degrees Fahrenheit.
Okay, so the picture is already way more complex than just a single down and back event. We've got cloud charging, an internal spark, the step leader down, a streamer up, the connection, and then that incredibly fast return stroke upwards, creating the heat and pressure for thunder. But the sources also make it clear that a single lightning flash isn't always just one single stroke, right? It can flicker.
That's another really key distinction the sources highlight. What our eyes perceive as one single flash or one strike is actually often composed of multiple individual electrical pulses or strokes.
Multiple strokes in one flash, how common is that?
Surprisingly common. The sources state that the majority of lightning flashes contain more than one stroke. A typical flash might consist of, say, 3 or 4 individual strokes. And one source even documented an astonishing case, a single flash containing up to 23 separate strokes.
23.
Yeah.
23 distinct pulses of light within what our eyes see as maybe a flickering half-second event. That's wild. What causes these later strokes to happen after the first big one?
They occur if additional negative charge can be made available from higher up in the cloud, feeding into the top of that original, now ionized channel relatively quickly after the current from the previous stroke has stopped flowing. This usually needs to happen within about 100 thousandths of a second or a tenth of a second.
So more charge comes down from the cloud.
Essentially, yes. This additional charge is brought down the channel by subsequent, often weaker discharges originating higher in the cloud, sometimes referred to as K streamers or J streamers, which basically feed more negative charge into the top of the existing channel, getting it ready for another go.
And before each of these subsequent return strokes, is there another leader phase? Is it like the step leader again?
Yes, there is a leader phase, but it's different. Before a subsequent return stroke can happen, a different type of leader descends down that existing channel. This one is called the dart leader.
Dart leader. How is it different?
Well, unlike the initial stepped leader, which moved in those discrete jumps, the dart leader is typically continuous and smooth in its movement. It just travels straight back down the ionized conductive path created by the previous return stroke.
What's his purpose then?
Its function is to deposit negative charge along the length of this existing pathway once again, effectively repriming the channel, getting it ready for the next return stroke surge upwards.
Is the dart leader visible, like the return stroke, or is it invisible like the step leader?
Generally, no, not to the unaided eye, for pretty much the same reasons we don't see the stepped leader clearly. Although dart leaders are also very fast, they move downwards at speeds around 1,000 miles per second, and their movement is smooth. They happen in very close time proximity to the extremely bright return strokes that follow them. Our visual system just doesn't have the speed or sensitivity to pick them out as distinct, dimmer events happening fractions of a second before the main bright flash.
So the sequence for these later strokes is dart leader zips down the old channel, loads it with negative charge again, and then, boo, the next return stroke shoots back up the same channel.
Precisely, that's the cycle. And interestingly, the dart leader usually tends to deposit late total charge along its path compared to the initial stepped leader, which had to carve a brand new path through insulating air.
Ah, so the later strokes might be less powerful.
Because of that, yes, the subsequent return strokes that follow a dart leader generally have smaller peak currents than the very first return stroke of the flash. Also, because the dart leader is just following the existing pre-ionized channel, these subsequent strokes tend to stick closely to the main trunk of that channel. They show significantly less branching compared to the highly branched first stroke, which followed the tortuous path of the initial stepped leader.
And what's the timing between these multiple strokes within a single flash? How fast does that flicker?
The interval between individual strokes is pretty short, typically in the range of 40 to 50 thousandths of a second, according to one source. Another gives a broader range, maybe 20 to 200 milliseconds thousandths of a second.
Milliseconds, so very fast, but maybe just slow enough to perceive.
Exactly. That interval, though brief, is actually long enough for the human eye to sometimes perceive the lightning flash not as a single event, but as a rapid series of pulses. That's the characteristic flickering appearance you might notice sometimes in a powerful strike. The total duration of a complete lightning flash, including all the strokes and the brief pauses between them, usually lasts around half a second in total.
So that half-second event we see as one strike could actually be this rapid-fire sequence of, say, 3, 4, or even more discharges. And here's another really surprising detail the sources mentioned about these multiple strokes within a single strike. They don't always hit the exact same spot on the ground.
That is definitely one of the most eye-opening findings from the detailed analysis in the sources. It really changes how you might think about the danger zone around a strike. Even though the dart leaders tend to follow the previous channel down, slight variations in atmospheric conditions, localized air resistance along the channel, or even just where the strongest upward ground streamer happens to form at that precise moment can cause these subsequent return strokes, all part of the same lightning flash, to terminate at slightly different points on the ground.
Hold on. How different are we talking? Inches, feet, or more?
Potentially much more. The sources indicate that the separation between termination points for different strokes within the same lightning strike can be quite significant. One source provides data showing the average separation distance is around 2 miles.
2 miles apart.
Yeah.
For strokes within what looked like one flash.
Yes. With a maximum recorded separation of up to 5 miles between the ground termination points of different strokes belonging to the same flash.
5 miles. That completely shatters the idea of a lightning strike being just a pinpoint event on the ground. One flash could potentially hit things miles apart.
It absolutely means the energy deposition can be spread across a significant geographical area, all from what you perceived as a single visual event. This could potentially explain instances where you see damage occurring at multiple locations, some distance apart, maybe several trees in a line get hit, or different parts of a large building seemingly from the same flash.
Wow. Okay, most of what we've talked about so far, the negative charge coming down from the cloud base, the return stroke, neutralizing, it sounds like what the sources call negative polarity strikes. And they're the most common, right?
That's correct, yes. The vast majority, something like 97–98% of cloud-to-ground lightning strikes transfer a net negative charge to the Earth.
The sources also detail a different, much less frequent type, positive ground strikes.
They do. While most strikes lower negative charge, the sources explain that occasionally a downward-moving stepped leader will actually carry and lower positive charge from the cloud down to the ground. These result in positive return strokes, and they transfer a net positive charge to the Earth. They are significantly rarer, making up only about 2–3% of all cloud-to-ground strikes.
So they're rare. Are they just different in terms of which charge moves, or do they have other distinct features?
Oh, they have several key differences highlighted in the sources that make them particularly important to understand. Firstly, positive strikes are generally described as being several times more powerful than typical negative strikes.
Oh, powerful.
Yes, significantly higher peak currents. They also tend to have a longer duration of current flow compared to negative strokes.
More powerful and longer lasting. That sounds inherently more dangerous.
It certainly can be. Another major difference is in their structure, how many strokes they have. Unlike the typical negative flash, which, as we said, often consists of multiple strokes, maybe 85% of negative flashes have multiple strokes, averaging around 5 or 6 strokes per flash.
Right.
Positive flashes, on the other hand, usually consist of just one single return stroke. The sources state that about 75% of positive flashes are single-stroke events. The maximum recorded is only 3 strokes in a positive flash. And if they do happen to have multiple strokes, the time interval between them is typically longer too, around 96 milliseconds compared to maybe 58 milliseconds for negative strikes.
So mostly single, powerful, long-duration strokes.
Yeah.
Where do these originate in the cloud, since they're bringing down positive charge?
Good question. Because they're transferring positive charge downwards, positive strikes typically originate from the higher positively charged regions of the storm cloud, often in the upper main part, or extending out from the anvil cloud.
Not from the negatively charged base like the common ones?
Correct. And interestingly, because of how charge is distributed on the ground, remember the induced positive charge is directly under the negative cloud base. These positive strikes originating from higher ups often have to travel horizontally for some distance away from the main storm core before they find a connection point. They frequently connect to regions of the Earth outside the main precipitation area, where the ground might actually be negatively charged relative to the upper positive region of the cloud.
So they can be more powerful. And they tend to strike areas further away from the heaviest rain or the main part of the storm. Areas you might think are safer.
That combination, greater power and potentially striking out of the blue away from the storm core, is a significant part of why they are so notable and dangerous. The sources specifically link positive strikes to certain meteorological conditions, too.
Like what?
They're more frequently observed in thunderstorms that have moderate to strong vertical wind shear. They can also be prevalent in specific environmental setups, like when cold air moves over warm water. Examples given include severe positive lightning over the Sea of Japan in winter, or similar situations like cold upper troughs moving over relatively warmer land in places like the western U.S. during spring and fall.
Okay.
And critically, they are most frequently observed during the later dissipating stages of a thunderstorm, particularly originating from the downstream anvil region, where that positive charge can extend horizontally for many, many miles away from the dying storm core.
So they're greater power, potentially longer duration, tendency to strike far from the storm core, especially from dissipating storms. These positive strikes sound particularly hazardous.
They are. And yes, they are specifically called out in the sources as being significant fire starters, especially in drier environments like the western U.S. This makes sense given their power and their tendency to strike away from heavy rainfall areas.
So when all this immense electrical energy, whether from a negative or a positive strike, finally reaches the ground through that channel, what actually happens to the Earth itself? The sources talk about the ground interaction.
Right. When that electrical pathway connects and the massive currents flow, an immense amount of energy is rapidly injected into the soil right at the termination point. The sources explain that soils act as the medium for channeling and dissipating these huge electrical charges.
How does the soil handle it?
Well, the energy is primarily conducted through the water content within the soil and also through the atmospheric gases trapped in the soil pores. This energy gets converted into heat, very rapidly raising the temperature of the soil and anything in it, like roots or moisture. It can also be temporarily stored or even permanently alter the soil's chemistry through breaking and reforming chemical bonds.
But the energy isn't just flowing down into the ground, is it? The sources mention effects happening right on the surface, spreading outwards.
Yes, that's a critical and extremely dangerous phenomenon known as surface flashover, or sometimes called ground arsing. Beyond just the current penetrating downwards into the soil, the intense electrical potential difference and charge exchange right at the strike point can cause a visible flash and electrical discharge to actually radiate outwards across the ground surface, spreading away from the initial contact point.
Like electricity skipping across the surface. How far out can that ground arcing extend?
The sources state that this dangerous surface arcing can extend quite a significant distance from the strike point, potentially up to 65 feet, that's around 20 meters.
65 feet.
Yes. And this is particularly likely to happen with very powerful strikes, say this carrying peak currents over 15,000 amps, and especially in conditions where the ground is saturated with water, making the surface a better conductor.
And this surface arcing spreading out 65 feet, that's a major source of danger, even if the main bolt doesn't hit you directly.
Absolutely. It is a primary hazard to people and animals who might be anywhere near a lightning strike point. It essentially electrifies the ground surface over a wide area, making any contact with the ground within that radius potentially lethal. It can also cause significant damage to shallow tree roots or buried utilities near the strike.
This phenomenon of surface arcing seems closely related to another really crucial safety concept the sources explain. Step potential or voltage gradient. Can you break that down?
Yes, understanding step potential is absolutely vital for lightning safety. Imagine the point where lightning strikes the ground as the bullseye of a target. When that massive current flows into the ground, it doesn't just disappear. It creates a distribution of electrical potential that radiates outwards, kind of like concentric rings or contours on a map.
Right. Rings of voltage spreading out.
Exactly. The electrical potential, the voltage, is highest right at the strike point, and then it decreases rapidly as you move further away. Now, if you happen to be standing within this electrified area and your feet are apart, even just a normal stride apart, each of your feet will be resting on a different ring. A ring with a different electrical potential, a different voltage.
Ah, I see. So there's a voltage difference between your feet.
Precisely. That difference in voltage between your 2 feet is the step voltage, or step potential. And because electricity always seeks to flow from higher potential to lower potential to equalize things, a current will flow through your body.
Through your legs.
Yes. It typically enters one leg, travels up through your torso, and then back down the other leg to your other foot, completing the circuit between those 2 points of different potential on the ground. Even if the main lightning bolt missed you completely, this step voltage can drive a dangerously high, potentially lethal current through your body because the voltage difference across just a foot or two can be enormous near a strike. The sources even give typical human body resistance values and show how easily a deadly current level can be reached with just a few thousand volts difference between your feet.
So that common safety advice you sometimes hear during thunderstorms, like if you're caught out, run away with only 1 foot on the ground, or shuffle away keeping your feet really close together, that's directly aimed at minimizing this step potential risk.
That is the exact scientific reason behind that advice. By minimizing the distance between your points of contact with the ground, you minimize the difference in electrical potential between those points. Keeping your feet touching, hopping on 1 foot, or shuffling with tiny steps ensures that both feet are on effectively the same potential ring, drastically reducing the voltage difference across your body and therefore reducing the risk of a dangerous or lethal current flowing through you from the ground itself.
Okay, that makes perfect sense now. Moving beyond the mechanics of the individual strike, the sources also discuss how all this lightning activity fits into the bigger picture, the context of the thunderstorm system itself. There seems to be a strong link between lightning frequency and type, and the storm's overall structure, particularly how tall it is.
There is indeed a significant correlation that meteorologists and researchers observe and use. The sources clearly show that higher rates of cloud-to-ground lightning activity are generally associated with thunderstorms that are more vertically developed, more intense specifically, those with taller storm tops. One source mentions that storms with tops reaching higher than 12 kilometers, which is about 7.5 miles, often show high CG rates, maybe more than 2 strikes per minute.
And the strength of the updraft within the storm, that rising current of air, seems particularly important for creating the charge separation needed for lightning.
Yes, the sources really point to the penetration of the storm's updrafts through the negative 20 degrees Celsius temperature level in the atmosphere as a critical threshold. This is thought to be the region where the primary charge separation mechanisms, involving collisions between small ice crystals and larger graupel particles or hailstones, are most efficient.
So stronger updraft means more ice collisions up there.
Exactly. The stronger the updraft, the more moisture and ice particles get lofted up through this crucial charging zone. This intensifies the charge separation process and consequently leads to more frequent and intense lightning activity. So intensified lightning is often well correlated with the strength of the updraft and, by extension, the overall severity of the storm.
Are there typical patterns for where the different types of lightning, negative versus positive strikes, tend to occur within a storm system?
Yes, the sources describe fairly consistent spatial patterns. Negative cloud-to-ground strikes, the common ones, are typically concentrated near the main updraft core of the thunderstorm, especially during its mature, most active stage when the updraft is strongest.
Okay, negative near the core. What about positive?
Positive cloud-to-ground strikes, as we touched on earlier, are more commonly associated with the later dissipating stage of the storm. They often originate in the upshear or downshear anvil region, that spreading cloud shield at the top, which can be horizontally displaced quite far from the main storm core. One source also highlights that in severe storms, lightning activity tends to be concentrated near key structural features, like the mesocyclone core, which is the rotating updraft associated with potential tornadoes, and also within zones of high radar reflectivity, indicating heavy rain or hail.
So given these correlations, can lightning activity actually be used as a reliable predictor of storm severity? Or maybe even specific hazards like tornadoes? The sources seem a bit cautious about that.
They do express caution, and it's important. While it's generally true that severe thunderstorms tend to have higher cloud-to-ground lightning rates and more organized lightning patterns compared to weaker storms, the sources emphasize that intense lightning activity doesn't automatically guarantee that a storm is severe or will become severe. Well, this is especially true in certain meteorological environments. For example, in parts of the western U.S., you can get high-base thunderstorms that produce spectacular and frequent lightning displays, but aren't actually severe in terms of producing large hail or damaging winds at the surface.
That's a really interesting point. The visual intensity of the lightning doesn't always match the ground-level hazard.
Exactly. And there was a particularly interesting, almost counterintuitive finding mentioned in the sources regarding tornadoes. In some specific storms that were studied, the cloud-to-ground lightning rates were actually observed to be low during the time the tornado was active on the ground. The CG activity only peaked after the tornado had dissipated.
Really? Lower lightning during the tornado?
In those cases, yes. Which suggests that, at least for those specific situations, CG lightning rates alone might have limited direct predictive value for the immediate occurrence of a tornado. However, the sources do still acknowledge that observing well-organized and frequent clusters of CG strikes can be an important indicator of significant convection, strong updrafts, and the potential for heavy rainfall or other impacts. So, using lightning detection systems and setting alarms for rapidly developing lightning hotspots is definitely mentioned as a valuable tool for weather forecasters monitoring storms.
Okay. One last specific visual thing people often talk about is forked lightning. When it looks like it hits the ground in multiple places at once. Is that just what happens when a strike has multiple strokes hitting different spots like we discussed?
Right.
Or is it something else?
According to the definitions provided in the sources, forked lightning is actually defined a bit differently. It refers specifically to a single lightning strike, one flash, although it could contain multiple strokes that makes contact with the ground at multiple distinct termination points simultaneously, or very nearly simultaneously.
So it's not successive strokes hitting different places over time, but the same initial discharge hitting multiple spots at once.
That's the distinction, yes. And the data presented in the sources is quite surprising here, too. It indicates that about 45% of all lightning strikes actually have multiple ground termination points.
Almost half. Almost half of all lightning flashes that hit the ground are actually hitting it in more than one place simultaneously.
Yes, that's what the data suggests based on detailed observations. So, from that one visible flash that might look like a branched tree coming down, there are multiple points where different branches of that discharge channel make contact with the ground at essentially the same time.
And can these simultaneous termination points in a single fork strike also be far apart?
They can be, yes. Just like the successive stroke termination points we talked about, these multiple simultaneous termination points within a single forked strike can also be separated by a significant distance. The sources provide data showing the average separation between these simultaneous points is around 1.05 miles.
Average over a mile apart.
Yes, with a recorded range from about 0.18 miles up to 4.5 miles apart for the different ground contacts within that single forked strike event.
Wow. So even a single flash, if it's forked, can be hitting the ground at multiple points that are potentially miles apart, all at basically the same instant.
It's yet another layer of the unpredictable and spatially distributed nature of how lightning interacts with the Earth. It really goes far beyond that simple initial image of a single bolt hitting a single spot.
Well, we certainly started this deep dive thinking about that common, simple image, the instantaneous bolt from the sky.
Hmm.
And wow, based on the incredible wealth of detail that in these sources, we've truly unpacked a process that is deeply complex, multi-staged, and incredibly dynamic.
Absolutely. We've traced the whole journey, haven't we? From the initial charge separation and those internal sparks high up in the cloud. We followed the path of that invisible step leader making its way down in those rapid jumps, explored the absolutely crucial role of the upward reaching ground streamers.
Right. And marveled at the unbelievable speed of the brilliant return stroke propagating back up the channel.
Understood how that intense heat and pressure generate the thunder we hear, learned about the likelihood of multiple strokes within just one flash, each potentially hitting different points, and even examined the unique and often more powerful characteristics of positive lightning.
And we really dug into how it interacts with the ground itself, that rapid energy dissipation into the soil, the incredibly dangerous phenomenon of surface earthing spreading out from the strike point, and that critical, often misunderstood threat of step potential, which can be lethal even if you're nowhere near the main channel hit.
It's just a profound reminder, isn't it, that what our eyes and ears perceive as this single quick event, that flash and boom, is actually the culmination of this rapid-fire sequence of incredibly sophisticated electrical processes. Processes happening across huge vertical and horizontal distances in the atmosphere and along the ground, all in fractions of a second.
Hopefully, taking this deep dive into the actual science behind lightning gives you, our listeners, a completely newfound appreciation for the sheer power involved, the intricate physics, and just the hidden complexity packed into that split-second display of nature's force. It's really a powerful manifestation of the fundamental forces shaping our atmosphere.
It certainly highlights how much fascinating and complex physics underlies even the most, well, commonplace, albeit dramatic, weather phenomena we experience.
And, thinking about all this detailed knowledge we've uncovered from the sources, how lightning actually behaves, the often unpredictable nature of its paths, the fact that different strokes within the same strike or different points within a fork strike can terminate miles apart, and the very real risk of dangerous ground arcing and step potential extending potentially dozens of feet out from where the visible bolt seemed to hit. What does all this science really tell us about how we should think about lightning safety? Or even about the design and true effectiveness of traditional lightning protection systems that often focus on just providing one single prominent point for a strike to connect to? It really does raise some significant and perhaps provocative questions about how we can best protect ourselves and our structures from this incredibly powerful, complex, and spatially distributed force of nature.